Hello, everybody. My name is Alexander Knüppel from the Technical University of Braunschweig, Germany. And this is joint work with Leon Scher and my advisor Ina Schäfer, also both from the Technical University of Braunschweig. So I want to talk about software contracts and their precision, so to speak. And in fact, we wanted to investigate whether mutation analysis can help us in this regard. Okay, but first let me start with the background. So this talk fully focuses on the paradigm that goes by the name design by contract. So if we think about object-oriented code and methods, contracts make the intended behavior of these methods explicit by using a formal language that is based on some kind of first-order logic. For instance, in this Java example, we have a sorting method, and by using JML, which is the Java modeling language that enables us to define a contract for that method, we can directly annotate in the code assumptions we have about this method and the properties it should fulfill. So here we have a precondition initiated by the keyword requires that defines under which circumstances this method is callable. And if the precondition is fulfilled, this contract guarantees us the defined postcondition using the ensures keyword. So why do we want to use contracts? Well, they can be used for various reasons, for instance, test case generation or one-time assertion checking. They can also be used for formal verification. So we could check if the sort method is compliant to this contract for any given input. And in general, it is a formal way to document the source code or the implementation. One important question in this regard is how good is our specification really? And what do we mean by good or strong specification? Methods can get quite complex, and specifying software is a very difficult challenge in itself. In this example here, which we will see again later, we have a set record method that also has a contract. However, it is not trivial to see whether the whole implementation is correctly covered by the specification. If we would apply some form of verification, we would actually see that this method is indeed correct, but only with regard to its specification. If the specification leaves too much room, this may give us a kind of a false sense of safety, for example. To make it a little bit more concrete, let's look at another example. In this case, a sorting algorithm, which is used by the standard library. And a classical problem is that we under-specify the actual behavior. In this case, we have only specified the sortedness property of this method, which means that when I call this method, I should be sure that the returned array is indeed sorted. However, that is obviously not enough. For instance, the method would satisfy this property if the returned array would only contain a random number of zeros. So what we additionally need is the permutation property, which states that the returned array is also a permutation of our input. The second version of this contract can be said to be more precise or stronger than the first version. Okay, why is that important? It is easy to overlook bugs otherwise, because our coverage of the implementation is not complete. Additionally, in design by contract, we have callers and callees, and I want to be really sure that I can meet the assumptions of methods that I call. In this example here, if another method wants to call the sorting method, but actually requires the permutation property, there's a mismatch between the contracts, and so applicability of the sorting method is very limited. And as a developer, I might be very interested in a metric or number that measures how good, strong, precise our specification actually is. And this number should somehow be connected to all the behavioral distinct implementations I allow with my specification. So the less implementations I allow, the better this value should be. So to illustrate this with the example of Venn diagrams, imagine we have a specification C1 and a couple of implementations that satisfy the specification. However, typically our goal should be to develop a specification that tightly fits our implementation. So if the prime implementation would be M2 in this example, we would rather want to have a specification that is closer to C2, which only allows the implementation M2 and not the implementations M1 and M3. Okay, let's go back to the set record example, which represents a real case. If we look at the specification and implementation, we notice a couple of things. First, the specification states that after this method is called, the field transaction counter is greater than 0. However, the implementation is in fact more precise because field transaction counter is actually incremented by 1, so it's really modified by this implementation. Another instance is that field empty is set to false. However, this field modification is not specified at all in the contract. This also leads to the fact that this class invariant may always be trivially true, depending on what we do here with the specification, but especially when we apply formal verification and actually trust the presented specifications. The reason is that set record is the only method that sets empty to false, and no other method has actually any clue that this is the case when we would abstract the implementation with its specification, as oftentimes done in the context of formal verification. So how do we identify all the behavioral distinct implementations that we allow given our specification? Well, first, it is probably not easy to get an exact value, as oftentimes the number will converge to infinity anyway, depending on how imprecise the specification is. But we have actually some concepts that could be exploited to systematically create behavioral distinct implementations. And one such concept is mutation testing or mutation analysis. And what we wanted to study in this work is whether mutation testing or mutation analysis might actually help us solve this challenge. So with normal testing, we try to evaluate how good our implementations are, right? And with mutation testing, we try to systematically create faulty versions of our implementation. And if our test suite cannot detect these faulty versions, then there might be some room for improvement. But in fact, we have found more implementations that our test suite would in this case accept. Essentially, mutation testing is based on two famous hypotheses formulated by D'Amelio et al., which are the competent programmer hypothesis and the coupling effect. So the first one actually states that faulty implementations are oftentimes very close to the intended implementation, but maybe some bugs that are actually easy to fix were introduced. So small modifications of the implementation may get us back to the correct version. Second one means, so the coupling effect, that we should concentrate on fixing simpler errors first. Again, mistakes that are not so far from the correct version, as they are present anyway, even if there are more severe mistakes. And I already teased it a little bit. There seems to be a correspondence between test cases and contracts. In fact, contracts may serve as test oracles used in test case generation, because their goal is to precisely specify the allowed inputs and the performed computations. So it is only natural to think about whether improving the test suite, which goes hand in hand with mutation testing, also presents a dual problem of improving contracts or the specification. So this work mainly focuses on this question, whether mutation analysis can provide enough feedback to identify instances of weak specifications and whether it can be used to quantify this weakness, which in fact may help developers get some insight about the quality of their specifications that they write. Okay, let's go back to the set record example. A possible mutation would be to discard the increment operator. In fact, that would even be an allowed implementation, as a contract does not specify the transaction counter. It does not specify that the transaction counter is actually modified. And this implementation is also not equal in behavior to the original implementation. So through mutation of the source code, we have identified a new distinct implementation, which also reveals that this specification is not as precise as it could be. Okay, so the main workflow looks like this. We have on top left our specified program, and we have also a predefined set of mutation operators. We then have a mutator that generates for the input program lots of mutants, depending on which mutation operator is applicable for the current input. And the mutants are then filtered, such that only behavioral distinct implementations remain, such that we have no duplicates in behavior. And finally, we employ a program verifier that is either able to automatically verify a mutant. In this case, we get a mutant that remains alive, or the program verifier cannot produce a correctness proof, in which case we mark the mutant as killed. And the ratio of alive and killed mutants gives us then a mutation score, which in theory should converge towards the precision of a contract. Obviously, converging towards that precise notion or quantification of a contract strength has a lot to do with the mutation operators that we apply. For the most part, we use fairly standard mutation operators, such as arithmetic or relational operators, so replacing or deleting them, but also operators that delete complete statements. Additionally, we also obtained some simple operators that we adopted from Hu et al. To mutate the specification, and that is something particularly interesting because when we think again about the duality between contracts and test cases, what does it actually mean to mutate test cases and what insights can we get? The operators themselves are very simple, and like the source code mutations only concentrate on small modifications. It is also clear that we only want to weaken preconditions, so allowing more inputs, and strengthening the postconditions, so to be more precise or closer to the implementation. And the question here is whether we can easily identify more precise specifications through these operators. So normally our mutation score would be the ratio between the generated mutants that were killed and all generated mutants. However, we do not want to mix source code and contract level mutation because the purpose slightly differs, which is why we created 3 distinct metrics that we used in our study. The first metric is the typical mutation score, where we only apply source code mutations, and this gives us a feeling for the precision of a contract. The second metric only tries to weaken the precondition. And this gives us a score that allows the developer to think about whether a weaker precondition would also make sense, because it would certainly increase the applicability of the method, or if the implementation is also something missing. Finally, the last metric only tries to strengthen the postcondition, and this gives us a score to what degree the method might be underspecified. And note, however, that we do not synthesize properties that are not specified, for instance, the permutation property of sorting methods, but rather this metric is an indicator on the properties and their strength that we already tried to specify and how good they are. To study the initial question, we have an implementation that is also open source and focuses mainly on Java JML programs. So the core of our framework resolves around MuJava, which is the mutation framework for Java programs that we integrated. And it already has the mutation operators implemented that we are going to use, except for the contract level mutation operators, which we added ourselves. And to evaluate the mutants, we employ the deductive program verifier key in version 2.6.3, which allows us to automatically verify JML programs. Okay, I will now present our evaluation, and for this we collected a total of 78 methods from various sources. More details on them can be found in the paper. And we did only use a limited amount of methods because we had to manually establish the ground truth, which means that in order to evaluate our framework, we obviously needed to know which specifications could be considered as weak, and that can take a long time. What is important here, we also only included methods that could be verified automatically. Otherwise, finding a more precise specification does not make really sense. In total, we formulated 4 questions. First, we wanted to know how common weak specifications are with respect to our subjects. Second, we wanted to know whether our framework is able to identify these weak specifications, and also what we can say about the mutation scores. Third, to address scalability issues with this approach, it is important to know which mutation operators could actually be ignored, as they do not contribute to the outcome. And finally, for the last question, we have a separate question for the contract level mutations, and here's a question if they actually make sense in this context. Okay, right. A short disclaimer here at the end. We have decided to not concentrate on scalability and runtime and such, as the research objective of this work was to conduct a study whether a mutation analysis is a valuable approach in the first place. So we acknowledge that our prototypical setup does not allow to draw conclusions about whether this is a scalable approach, and we could certainly not justify any claims we would make in this direction in terms of generalizability. Okay, to start with the first question, we have a couple of values here in this table. And on the right side, we illustrate what we identified in our manual search for weak specifications. In total, from the 78 methods, we identified 28 methods that can be considered as too weak for the intended implementation. We can also see that our mutation analysis is able to identify 21 of these 28 instances. Here, we only use the source code mutations. The mutation score that we illustrate here is the arithmetic mean of the mutation scores of every method per project, but gives us some insights on how well a particular project is specified. For instance, the bank account case study has an average score of 0.56, which is very low compared to the other projects. And in fact, many contracts in this case study are fairly imprecise. To follow up with that investigation, we conclude for our second question that a mutation analysis is able to automatically find instances of weak specifications. We also identified that the more complex a method is in terms of constructs used and the general size of the implementation, the more likely we are able to find such instances. Mutants have also the advantage that when we find a mutant that remains alive, we have a direct instance of an implementation that is also covered by our specification. And that instance can be used for further investigations, probably manual inspection by a developer. Also, this is only our gut feel, and this needs still further investigations. But based on our manual analysis of all methods and contracts, the mutation scores reflect adequately well which specifications need more work and which specifications are already pretty sufficient. So all in all, we think that following this line of work is promising. The third research question aims at identifying a significant useful subset of mutation operators. So we have this figure where we illustrate each source code mutation operator on the x-axis and the ratio of alive and killed mutants in percentage on the y-axis. Only one operator produced 0 mutants, which is LOD, and that has to do with deleting the bitwise complement operator, which, to be honest, is rarely used and was not present in our subjects. However, we also acknowledge that if we would have a significant amount of subjects with bitwise operators, these are a great source of introduced bugs. So, but for these subjects, we identified a total of 6 operators actually that were pretty effective and in fact would lead to very similar mutation scores while also generating only 50% of the mutants compared to applying all mutation operators. However, we need to be a little bit cautious here. We can only draw conclusions with respect to the subjects that we used. Finally, we wanted to investigate if the contract level operators give us adequate insights on the precision of our contracts. On the left side, we illustrate a graph where we again depict the projects on the x-axis and the number of generated mutants on the y-axis. We further illustrate 3 categories, namely live mutants that could either be considered as having a too strong precondition, which is here depicted in yellow. So we could in fact weaken the precondition and the implementation would still work. Or a too weak postcondition in blue. So we could make the postcondition or some property more precise. And finally, the killed mutants in green, which means that the stronger contract we generated was too strong for the implementation, which is actually the desired outcome. What we can see here is that weakening the precondition is oftentimes possible and therefore complements the source code mutation, which does not really address this issue of a precondition that is defined potentially too restrictive. The strengthening of the postcondition, however, was only possible in 1 or 2 instances in the PayCard case study. And we saw an example, which was the set record method, actually. In our manual analysis, we also identified that too weak postconditions were often due to missing properties or missing field modifications. And that the properties that were specified were actually adequately precise. And this is a problem with this operator here because these instances are obviously not caught by the PS operator. So all in all, weakening the precondition with our operator makes sense. Strengthening the postcondition did not make so much sense here in our evaluation. So all in all, we set out to study whether mutation analysis may help developers to quantify the quality of their written specifications, for which we implemented and presented a fairly simple framework. And in our evaluation, we found out that weak specifications occur in many subjects and can also be identified automatically by mutation analysis, which shows that this is worth to be developed further. Obviously, we are relying greatly on heuristics, but the vision is that as developers working with written specifications, we can somehow integrate such a framework into our development process, having it running on the side, incorporating it into our continuous integration, and really think about new metrics that may help us to quantify the quality of our work. And we think for that vision, this work is a great starting point and can also be used for benchmarking in the presence of new approaches which are better and more scalable. So this concludes my talk, and thank you very much for listening.
Okay, many thanks, Alexander, for your talk. We have already a question, and the question is from Marie-Christine Jacob. How do you deal with equivalent mutants? There is some problems. It seems that nobody is in the room.
Hello, everybody. My name is Alexander Knüppel from the Technical University of Braunschweig, Germany. And this is joint work with Leon Scher and my advisor Ina Schäfer, also both from the Technical University of Braunschweig. So I want to talk about software contracts and their precision, so to speak. And in fact, we wanted to investigate whether mutation analysis can help us in this regard. Okay, but first let me start with the background. So
there is nobody in the room. We have a couple of questions for him, but we have not the author. Aina, could you please answer to this question? So we have two questions. So I think that you have to unmute your microphone. So the first question was, how do you deal with equivalent mutants?
Hi, Stefania. I'm very sorry. Alex actually was supposed to be here, and I assume technical problem. I'm not sure you can see me now.
Yes.
So the question of Marie-Christine, how do we deal with equivalent mutants? Of course, that's always a problem when we are looking at mutants. We did that manually. So actually in the evaluation, Alex did that manually, and that is an orthogonal problem that we would have to look at in future work. How to deal with equivalent mutants. We didn't, the plain answer, honest answer is we didn't do it this time, but we did do it manually.
Okay, so the other question from Lucas Ambost. So did you notice any changes in the verification time of the mutants?
Okay.
Alexander, yeah.
Okay, I'm very sorry for that. Sorry. I'm very sorry for that. Let me see. How do you deal with equivalent mutants? I can answer that very quickly.
I have answered the equivalent mutants already. You can say something about the changes in the verification time for the mutants.
Actually, we have not looked into that really. I think they were pretty much equivalent in terms of time, so we didn't notice any changes there. But once again, the mutant operators are very simple, and the examples themselves were also very small. So verification time didn't matter actually at all. So most of the tasks were solved in roughly 1 minute, 1.5 minutes. So we didn't really look at that. Yeah. But obviously, this is a problem if we employ a deductive verifier for that. We had no mutants that timed out, but what we didn't look at was if we could also maybe use something like assertion checking or test case generation, which would maybe solve some of these issues with deductive verifiers, but would come out with other problems, of course.
Okay, thanks. We have no time for another question. The time is finished now, so it's sorry.